Energy cannot be created or destroyed. The first law of thermodynamics guarantees strict energy conservation across any system, but there is a glaring omission in this principle. The first law is mathematically agnostic to the direction of time. It tracks the joules, but it does not dictate which way a natural process actually flows. Drop ink into a glass of water, and it violently disperses into a complex swirl. Gathering that ink back into a perfect sphere wouldn't violate the first law's energy conservation rules, yet we know it never happens. Physical processes move strictly in one direction. Physics was forced to confront this directional blind spot during the industrial push to convert thermal energy into mechanical work. Building these early macroscopic heat-to-work converters exposed that heat moves from hot to cold, never the reverse on its own. Mastering JEE Advanced Thermodynamics relies on treating the second law as a mathematical filter for reality. The first law tells us what exists. Only the second law tells us what is possible. This filter operates through two boundary conditions. The first is the Kelvin-Planck statement, governing heat engines. It dictates that it is impossible to construct an engine that converts all absorbed heat directly into work. Mathematically, the efficiency must always be strictly less than 100%. The reciprocal constraint is the Clausius statement, which governs refrigeration. Heat cannot spontaneously flow from a colder body to a hotter body. To force thermal energy against its natural gradient, you must input work from an external source. When applying these laws, two major illusions destroy scores on the JEE Advanced exam: equating adiabatic with isentropic, and defining entropy merely as a measure of disorder. These mathematical constraints act as the tripwires built into high-level cyclic thermodynamic problems. Discard the messy room analogy for entropy. It is useless for advanced populations. Entropy is the degree of energy dispersal within a system. We quantify this by counting the number of accessible microstates, denoted by omega. This statistical framework was established by Ludwig Boltzmann, whose work anchored our understanding of thermodynamics to the actual behavior of particles. Here is Boltzmann's microscopic relation. S equals Boltzmann's constant times the natural log of omega. Macroscopically, this translates into the integral equation. ds equals reversible heat transfer divided by temperature. Measured in joules per Kelvin, entropy is an extensive property. It is a state function. Whether a gas expands isothermally, drops in pressure, or follows a chaotic path between state A and B, the total change in entropy is exactly the same. It is path independent. Treating entropy strictly as a state function resolves the complexity of cyclic problems, where path-dependent heat and work variables fluctuate. This brings us to a frequent structural error, assuming that the entropy of a specific system can never decrease. If you compress a gas or freeze a liquid into a solid, the energy dispersal of that specific system drops. Its entropy strictly decreases. The second law dictates that it is the total entropy of the isolated system, the universe, that cannot decrease. We calculate this by tracking heat transfer. As heat moves from the hot reservoir, its entropy drops. But as the cold reservoir absorbs that heat at a lower temperature, its entropy rises by a larger margin. The sum yields a net positive increase for the universe. If we execute this perfectly and infinitely slowly, maintaining thermal equilibrium, the drop mirrors the rise. The change in the entropy of the universe equals zero. This is a reversible process. For any real, spontaneous process occurring at a finite rate, the change in the entropy of the universe is strictly greater than zero. Calculating the net change in universe entropy serves as the mathematical proof for whether a process described in a JEE problem can actually occur. A dangerous trap in problem solving is assuming that every adiabatic process, a process with no heat exchange, is automatically isentropic, or constant entropy. That assumption only holds for a perfectly reversible, infinitely slow adiabatic expansion. On a TS diagram, a reversible adiabatic process maps as a straight vertical line. Since heat transfer is zero, entropy on the x-axis remains constant. But apply this assumption to the free expansion of an ideal gas into a vacuum, and the calculation will fail. In a free expansion, work and heat exchange are both zero. According to the first law, internal energy remains unchanged, meaning for an ideal gas, the temperature is constant. Yet, because the gas now occupies a larger volume, the number of accessible microstates increases. Despite zero heat exchange, the entropy of the gas increases. We calculate this change using the ideal gas formula. Delta S equals nR times the natural log of V2 over V1. On the TS diagram, the state moves strictly to the right as entropy increases at a constant temperature. Irreversible adiabatic processes are not isentropic. Due to volume expansion or internal friction, they inherently generate entropy. To map the theoretical limits of thermodynamics, we look to the Carnot cycle. It acts as the mathematical ceiling for engine efficiency. It consists of 4 reversible processes: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. Analyzing this requires dual diagram mapping. We trace the cycle simultaneously on a pressure-volume diagram and a temperature-entropy diagram. Notice the unique geometry on the TS diagram. Isothermal processes are horizontal, and reversible adiabatic processes are vertical. It resolves into a perfect rectangle. The area inside represents the net heat transferred, which equals the net work output. This brings us to Carnot's theorem. No engine operating between 2 thermal reservoirs can surpass this efficiency limit, which is calculated entirely by their temperatures. Warning tone. When calculating this maximum efficiency, you must use absolute temperature in Kelvin. Using Celsius will immediately invalidate your answer. The Carnot cycle defines the universal geometric boundary against which real-world thermodynamic processes are measured. When we transition from that theoretical boundary to real irreversible engines, the performance drops. Internal friction, gas mixing, and heat transfer across finite temperature differences degrade the cycle, shrinking its efficiency. We can visualize this inefficiency mathematically on the TS diagram. The real engine traces a smaller, distorted cycle inside the Carnot boundary. The difference in area is the entropy generation. That red gap explicitly represents lost work. It is the mathematical proof that maximum work output is exclusive to perfectly reversible processes. Entropy generation is not an abstract concept. It is the direct, quantifiable measure of a system's irreversibility and its lost mechanical potential. Your strategy for IIT JEE Advanced Thermodynamics requires synthesizing these principles. First, use the first law to track energy conservation through state and path functions. Second, use the second law to verify that the change in universe entropy is greater than or equal to 0, proving the process is physically feasible. Do not blindly memorize equations. Before applying any formula, identify if the system is isolated or closed, and confirm if the process is reversible or irreversible. Mastery of thermodynamics means recognizing that the second law defines the mathematical boundary of the physical world.